Somebody wants to ask a question, you should do.
Shall we start probably?
Yeah.
So it's a pleasure to have Oleg Andreev. He'll be visiting us for the rest of the week from our review. So tell us about strings and multiquark hadrons.
Okay, thank you for having me here in New York City. I just want to give you some ideas about 3 stories. It's written in this paper, 2 published and 1 in progress, but will appear soon, I hope, next month. And that's about 3 kind of doubly heavy hadrons. Doubly heavy means that each of those has a pair of 2 heavy quark sources. It's either quark-quark or quark-antiquark or maybe antiquark. And the main candidates for such hadrons is CCC, TCC, ZB. These 2 first were discovered quite recently at CERN, at LHCP collaboration, and the second is from Japan, from Bell. I will use the hadroquarkonium picture mainly promoted by Voloshin and Kosas. And the point with this picture is that consider light quarks, because relativistic, as a kind of clouds or medium. And inside of this medium, there are heavy quark sources. So because it's only 2 heavy quark sources, the energy of any of this configuration is a function of the separation between the heavy quark sources. So it's all times denoted by L. That's I'm interested in this. And the first example is doubly heavy baryon. And in this case, you know the quark model well in 4 dimensions. If you just want, the point. Sorry, I missed that. The point with this picture that because heavy quark are very heavy, they are non-relativistic. So those 2 guys are non-relativistic, and then idea is quite transparent. If one can compute the energy as a separation between these heavy quarks, then the next step is just solve the Schrödinger equation with such a potential to get the energy levels. So very similar to the Cornell model for quark. And in 4 dimensions for the doubly heavy baryon, there are in fact 2 basic configurations. So I just remember that heavy quark sources, light quark, and then at least the stringy configuration means that one can really connect this with a here's string junction, because I assume that the number of colors is 3, it's LQCD. So only 3 strings meet together at the string junction, and that's a string picture of baryon. It's known from the 60s last century. And another disconnected configuration looks like this one. And what happens really with this configuration, that's due to production of light quark pair, one of the string got broken, and baryon decayed into 2 really hadrons. One is a heavy light meson and another heavy light baryon. It turns out that it's enough of only 2 string configuration to describe the ground state of the system. I will be interested in this case. You know that you're not ground state of the system. But this picture becomes quite funny from 5-dimensional point of view. I will use this ADS QCD approach. It's effective string model in 5-dimensional space. space usually is just deform ADS5, and the deformation, this factor, the O factor, is the simplest deformation. And its motivation for such a deformation is twofold. The first is just phenomenological interesting deformation, and the second point is it just allows many things compute analytically in the geometry. So what happens with the first configuration? The first configuration, and in fact how to really get idea about it. So one put all the system on the boundary of this ADS5 space, boundary at r equals 0. But if you put it as a heavy quark are infinitely heavy, so they're at rest. But all other, I mean strings, the string junction and light quark will be pulled out into the interior by the gravitational force. So the configuration becomes like that. And the point with that it's valid only for small separation between quarks. What happens next is that the string junction of baryon vertex gets up and hits the light quark. So it will be something like that. It's kind of defect, only two strings now, and these two strings meet this defect. And for even larger separation, happens like that. It's again defect, but point that in the geometry there is a notion soft wall, and soft wall is a really it's a model of confinement. Means that string can get deeper into the interior than this soft wall, and soft wall is quite easy. It's just a local minima of this potential. So it's at 1 over the square root of s. Let me just give you idea that potential for ADS, pure ADS, the potential is proportional 1 over r square, but with the deformation going like this. Soft wall. So strings come from here, and clearly it stops exactly at soft wall. Energetically not favorable going further. And it's possible to check that this picture works at least for the heavy quark anti-quark systems, so it works here. And as a result, in the first case, the energy is a piecewise function of separation, so it's made of 3 different pieces.
Sorry, so the light quark doesn't have to live on a brane. It can be
No,
anywhere.
that's a good question. Let me explain. You know, point that there is some wisdom that there is a duality between brane configurations and background configurations. For example, for ADS 5, how it appears, it's a large stock of deep 3 branes, right? And this large stock gives you ADS 5 geometry. It is the same. You can consider branes for light quark, or you can introduce scalar background like an open string tetraquark background. That's what I will do. And in the simplest case, with this background constant, it just gives you the quark masses. So it means that you get something like M ES, right? As an integrity. Here, just substitute this geometry I am using, and this parameter is related with like dimensional mass, but it becomes dimensionless because combined with ADS values. And what happens with this? That means that appears here. So due to the gravitational force, there is force here, but also string tension here. And position is defined by the equilibrium between one force and another. You can see it directly from the action if you vary with respect to the position of work, the field dimension. So total action vary. And that gives you the force balance equation. It's practically it's much more convenient than introducing branes, because if you change geometry, for example, to the black hole, I can see what happens at finite temperature. But to solve the supergravity equations, this is supreme configuration.
What the assumption about the mass of the junction? Because
oh, that's a good idea. Another point. Another point is that really idea comes from 10 dimensions. And then by different. So in 10 dimension, string junction baryon vertex is D5 brane wrapped on the internal space. So usually you have ADS5 cross S5, but here of course deformed ADS5 and this kind of person. So it's D5 is wrapped on this internal space. And from 5-dimensional perspective, it looks like point-like object, right? But still, it's possible to get idea about the action for this from 10 dimensions. Volt volume. But again, one has to pay for that, saying that we don't know about this guy nothing. So it's just saying that it becomes some free parameter times dt, and some functions that depends on r, and the form of this function. So the only free parameter is the prefactor.
but it's more like a heavy thing, right? Because it's no.
It's more funny. It's mainly defined in terms of the Ramon fields, not by gravity. So it looks like anti-gravity. The gravitational force acts on the vertex is bounded. So it's not really gravitational force, it's Ramon, but nobody knows how to show this explicitly. I found that it's negative just by comparing with the latest result for pure Young Mills. And it turns out that this guy coefficient is small, something, but negative. Of course, one can say that it's a negative tension brane, but I don't know. Probably it's just additional force from 10 dimension, light colors. That's not me. Okay, and now let me just say what happens with this two this disconnected diagram, and then for the heavy light meson it looks like that. So heavy quark on the boundary and light anti-quark in bulk, and for the heavy light baryon looks like this. So the strings in question here really is just simple Nambu-Goto strings, and as I already told, for the baryon vertex for string junction action is like this one. So this guy comes from this D5 brane, but tau I treat as a free parameter of the model. And the same true for the light quark. Yeah. So this guy, as I told you, just comes from geometry, but prefactor, it comes, of course, like a mass in 5 dimensions, but I will treat it as a free parameter. And really, there are 4 parameters in this model. 4 parameters. S, deformation parameters of the geometry. G, it's related with Nambu-Goto string, it's ratio R squared, ADS 5 radius over alpha prime parameter. And then kappa K, that really parameterized the vertex. And N, it's parameterized the quark masses. And all these parameters more or less known from the other things. So what I tell you is just predictions. Now, first exercise, of course, see that the connected configuration gives you reasonable function. And that's indeed the case. It's for 2 different values of k, so it's indeed suggested here. And the most important point is that one can check the heavy quark by quark symmetry. So for small L, it behaves like this one. So it's factorized into two pieces. The first term is the quark potential, and the second is just the heavy light meson. It's this configuration. So it's automatically one can check, not numerically but analytically. And now, of course, the main question is still not the potential for the system, the ground state, but it's just only energies of two string configuration. So how to get the potential from those? And I follow really the latest gate theory approach. So it's used to describe string breaking Q bar system. And point one has to introduce the model Hamiltonian. So the diagonal terms are given by the energies of string configuration, but there are non-diagonal terms. It's a kind of superposition for this two-state system. And of diagonal terms describe mixing between these two configurations. So the potential is just the smallest eigenvalue of this model Hamiltonian. And point important, it's easy to solve quadratic equation to find explicitly. Point that one can introduce important scale, string breaking scale, just equating the diagonal terms. So it looks like this one. And the first, of course, depends on the quark separation, and the second is constant. And if so, then let me show you what happens. Point that now this energy for the connected configuration, this two disconnected, and the potential looks like as it should be. So here gets flattened at some scale, and this scale is called the string breaking distance. And interesting, of course, make an estimate of this guy, and to do so I will fix the parameter n, this one to describe light quarks, by saying that for the QQ bar system it reproduces the latest results by Bulava and co-authors. If I do so, I will get that in my case it's roughly the same. You see very little difference between two. So the string breaking really happens in this small Q system in the double heavy baryon. That's important factor. That's first story. So it's like that. Only string break. Now let me go further and discuss more complicated story. More complicated story, two heavy quarks and two light anti-quarks. It's very popular was during last year because in CERN they discovered TCC meson recently in last September, and it was big activity there. But of course, in theory, people try to make predictions for the mass of this meson from the 80s last century. That's funny or something. But finally, it was discovered. But in this case, in 4 dimensions, there are only, again, it's luckily only 2 configurations. It's connected one. I will call it as a compact tetraquark, and disconnected one. And disconnected is just a pair of 2 mesons. And then important point that this guy works. So there is only one disconnected configuration possible. And my claim that only this configuration contribute to the ground state potential for the system. Again, picture of course becomes more complicated in 5 dimensions. Now we have 4 pieces, and for small, again, it's quite easy to suggest from this one everything in the interior except the heavy quarks, so it looks like that. But then what happens vertex goes up and hit the anti-baryon vertex, and then they organize kind of brain-anti-brain pair. Then they go up further and hit the light anti-quark. And finally at large L, so L is near infinity, the strings approach the soft wall. So the configuration.
Sorry, but these are the same, is the same configuration in all the pictures?
No. It's for two small.
So one is Q bar and the other is Q bar. Right?
Yeah. So it's now four quarks here. Before we have only one light, and now two.
But in these two rows, it's two different configurations.
Yeah.
And why can't they form mesons? I mean, the QQ bar.
No, it's tetraquark. It's meson because 4 quarks spin is integer.
Yes, but I mean, why the QQ bar cannot break off?
QQ bar, that's another story about QQ bar here. I see your point. That I'm interested only in the ground state. Of course, there are much more configuration. If you are interested in the excited states, then you should add more and more. But I'm interested only in the ground state because the tetraquark structure appears for the system at the level of the ground state.
But I was confused. In your pictures below, you have a little q without a bar.
Sorry, that's I see. Okay. And for the disconnected, we already have it here. This one, it's the same. And again, to find now what happens with the potential, one can again define the effective Hamiltonian with the diagonal terms and off-diagonal terms. And the critical separation distance now defines by this guy. So it's something like that. And that if estimated what happens that the critical separation distance is very small really. It's of order 0.2 Fermi. And why is small? Because it's absolutely different physics behind of that. What physics? It's physics of string junction annihilation instead of string breaking. What happens with this guy? It's vertex, baryon vertex annihilates with anti-baryon vertex. And then due to that appears a pair of mesons. It's most clear in this here. This guy annihilates with that, so it gives only one possibility. And then surprise is that the scale is factor 5, 6 smaller than the scale for the string breaking. So string breaking is 1.22, but this guy is only 0.2 Fermi. And the picture for the potential looks like this one. And of course, if you know the scale for smaller distances, the system looks like a compact tetraquark, but for larger systems, it's a molecule made of 2 mesons.
So it's never stringy.
Only here. That's nuclear physics. Exactly. But surprise, why nuclear physics appears not at scale 10 Fermi, but 0.2 Fermi. And possible answer is that because it's not vacuum, but it's in a cloud of light quarks. So that's another point again. Also, this is compact tetraquark. Compact. This object is really compact. And then there is interesting phenomenological story here. Moment. Still before that, let me also tell about the relation. As I show you these diagrams. Look, I mean, this one, for example, looks very similar, roughly, to that one, right? So it should be relation between the potentials, but it's also dictated by heavy quark quark diquark symmetry, and this relation, this one. So indeed, this for 4-quark system and 3-quark system, there is just only shift due to the baryon and meson, and this well defined because it doesn't depends on the heavy quark masses. It's really one minus another, and due to the symmetry, it's valid only for small separations. So for small, that's what we know, and it's possible to check it's numerically this relation in the model I'm doing, and see that indeed for small separation it's perfect agreement, but then there is a gap between two. But this gap is not very big, it's order 40 maybe. But now what we learn, that this picture is wrong, because for this guy one has to take into account string breaking, but for the second string junction annihilation, if one do it, what happens is this guy is going like that. It's already at point to Fermi, but for the baryon it's going like this. And so my claim that such a relation is valid only for separation, at least in this model, which I follow the latest parameterization, only for separation smaller than 2.2 Fermi. That's just refinement for the heavy quark diquark symmetry. So one really should be very careful here. And now about phenomenological application. Phenomenological application is really about the mass of the TCC meson. You see, one can use this relation between the energy or potential. It was used in fact in the infinite heavy quark masses limit. You can just say that the same relation should be valid for the hadronic masses, because the spin interaction is suppressed by 1 over mq heavy quark mass. And if so, then there were estimates by two groups really, Eichten and Twig, and then Karliner and Rosner quite recently. And they really made very good estimate of the mass of the TC meson. But from what I have told you,
Sorry, TC means that capital Q there is actually C quark, right?
Yeah.
Which is very far from being infinitely heavy, right?
Yeah, that's true. That's another point also, but still it works. This, I mean, this relation formally it works. If you know what to substitute, which lambda and d mesons baryons, then it works. Probably it's because of difference. You compute really some differences. And the point that if the estimate is true, and what I told you also true, that means that this guy TCC is indeed compact, because this relation is valid for very small quark separations. Just string evidence for this meson TCC is compact tetraquark. Otherwise, that relation is broken by the string junction annihilation process. Even not the string breaking, but the string junction annihilation. That's exactly this scale of the string junction annihilation. So it's the evidence that's indeed it's compact tetraquark. Again, and now the most complicated story. It's about ZB, and it was discovered Bell collaboration roughly 10 years ago, but the system is much more complicated. Why? I will tell you this about this guy. So now two and due to that, the life becomes hard. In 4D, there are at least two disconnected configurations. Now one can connect heavy quark with a heavy antiquark or heavy quark with light antiquark. So two configurations. And the same happens with connected. So connected formally one, but still appears another disconnected configuration, and then it comes from configuration A as a string breaking here, you will see. And my claim that these four define not only the potential, I mean the energy of the ground state, but the energy of the first excited state V1, and tetraquark appears in this system here at the level of the first excited state. So no tetraquark at the level of the ground state. It's quite different.
So this D just corresponds, you just added QQ bar to B, right? But also you can think about it the same as D is B with added extra.
Oh, you can, equivalent, no, of course you can think it as a PS virtual part for this.
But why before this configuration, this kind of configuration played no role in previous systems?
No, in previous system was only one. In previous system, if you have a quark, you can only connect it with light anti-quark. That's the point.
Right, but you can always add to whatever you have. You can
that's
light
true.
QQ bar,
But that you will get to the excited level.
And why is it? But this is.
And here exactly will be ground state and the first excited level. And there's just point to consider this guy because connected configuration contribute to the first excited level only.
I see. So the leading order like this kind of string breaking of connected one.
No. The leading order, that's another string process. It will be string reconnection process.
But you're saying that the configuration we care about, it kind of mixes naturally with excited state.
Exactly.
With the ground state. That's why it's.
Okay. And now, of course, easy to do the first two. So the first is just you can consider as a pair of heavy quark and antiquark pair in a pion cloud. This guy is a pion system, so it looks like that. And the second, as I discussed previously, is just a pair of mesons, so it's in 5 dimensions like this. And this here, there's non-trivial thing from the latest gate theory that can compute this point that it's amazingly that energy is just sum of these two different. So pion mass plus this energy of the quark and antiquark mass. Why this happens? Because really it assumes that one average over the position of the pion here. This pion average over all the lattice, and then the answer is just shifted. And for example, for the Cornell model, just shifted by some constant which identifies the pion mass. That's not trivial. Okay, but what happens with this guy? It's interesting point. Now, point that at small you reproduce it like that, but for larger separation, it looks like a D-quark, anti-D-quark system. So this guy is really going in the opposite direction, and then you end up with this and that. And then for very large, this approach quark and vertex approach the anti-quark, heavy anti-quark. So it's the quark picture appears naturally. And for the last diagram, if you know about the pion, it's just two mesons and pion here. So it's not very difficult. Now let me show you what comes out. That's for the system I have and for the parameter values. You see, the ground state comes from the first A and B diagram, this and that. So it's here looks like this, and then it's going like that. And it introduced a new scale, and this scale is string reconnection scale. That's what happens with the string reconnection scale. You have two strings, and then like so, for example, here it was Q bar, Q bar, and then it becomes what? Q. That's another scale, the set scale, which appears as a string reconnection scale. And the scale, that if you estimate it something like also point to Fermi, but point here that this scale is dependent on the pion mass, so this pion mass. And still this scale is a bit larger than Z for the string junction annihilation. So the string junction annihilation. So for the first level, going like this. Here happens string junction annihilation, then small flat, and then string reconnection, going like this, and then string breaking, 3 scales. And then, of course, point that the ground state energy is defined in terms of 2 configurations, but the first excited state is defined in terms of this compact tetraquark configuration, the first, and then all this bunch of others. So it's a novelty that tetraquark occurs at the level of the first excited state in the system. That much more difficult becomes a problem. And formally, again, I can introduce 3 scales, just equating the diagonal elements of the effective Hamiltonian. That's, I already showed you that string reconnection scale. That's a string junction annihilation. And then string breaking again. And now that's what I told, that's effective Hamiltonian. This guy I equate with this. An interesting point that hierarchy looks like this one. First, string junction annihilation, then string reconnection, and then string breaking. But one can, of course, improve the picture by introducing more reasonable pion scale. The problem that this string model doesn't describe light hadrons, only hadrons with one infinitely heavy quarks. So something must be on the boundary. So what happens with this guy if I estimate? Give us pion energies of 1 GeV. But on the lattice, it's only for the parameter I'm using 280 million. That's problem. And now let me just take this guy as another parameter of the model, and then picture changes. You see what changing that now string reconnection happens at distances a bit smaller than 1 Fermi with the pion mass as on the lattice. It's twice heavier as the real pion, and the whole picture for the 2 potentials here. So the ground state, this one, so it's only in terms of mesons. Here, just heavy light mesons, but here it's Charmonia, if you want, in pion cloud. But for the
why don't use physical pion mass here?
because on the lattice they use, I follow to fix other parameters. I follow the lattice, so they use not very fine lattice, mass twice larger than the physical one. So it will be inconsistent if I just, you can of course substitute this guy 140, but it will be not consistent with others. Like, I mean, the string breaking distance is heavy quark potential.
But then you want to compare it to real world.
That's no, that's true.
Where the mass is.
Yeah, no, that's true. There is another choice for the parameter values, more physical. But if gives more or less the same. Picture the same. That's not my point. Is this picture how it looks like. So again, for the ground state is here, and it's the main scale is just string connection. And the compact tetraquark, this guy, ZB, appears only again. It's compact. It's funny that's again it's 0.2, something like that here, and then it's molecule made of 2 mesons. Then it's becomes harmonia in a pion cloud, and then finally it brings in 3 different mesons. So that's fun with ZB systems. Okay, thank you. That's tell you.
Thank you. What here actually there is people are interested also in hexaquark. What can you tell something about whether you expect them to exist?
About
6 quarks.
6 quarks. Baryons. No, that's still for me it's complicated, but very similar technique. I hope that's my next project is applied for pentaquarks, for doubly heavy pentaquarks. I mean, what happens with deep baryons, that's another story. But for this, again, that stringy picture gives you just proof that if tetraquarks exist, they compact, really compact, unusually compact, because the nuclear physics goes up to very small scales, and then only PCD. Or roughly, you can think of that. Take 2 mesons and try to really press one to another. You do it still at bound state of 2 mesons molecule, but at some point appears this funny PCD-like interaction, so it really will be 4-body interaction between 4 quarks.
But there's some, if one adds now some angular momentum, is there some kind
Oh,
of...
that's I don't know. It's another problem. The problem I am doing the static limit, like latest QCD, so very heavy quarks, and if you try to do this angular momentum, will be much more complicated.
Basically, the question: does one expect to find the whole rigid trajectory associated?
No, it should
so
be.
then they will be not so compact, right?
No, of course. If you use, but usually if you do a rigid trajectory, this picture is lost because you get picture like this diquark, something like that.
Right.
This guy will be. So from this point of view, if you use angular momentum, it's just a way to get dipole picture. But you will pay for that because this picture is really, whether it's tetraquark, I mean configuration, don't do us.
Too bad Marek was here last week. So
I know. Kobe told me.
Yeah, he's at Stony Brook right now. So.
Right. Oleg was at Stony Brook.
Because Marek will be back. He's around for like a few weeks, but he's taking a break to this.
I see. No, Kobe told me about it.
But you might overlap here because you're here for the rest of the week.
Oh, you're here for this week, right?
Yeah.